Hello, in this lesson we are going to derive the equations of transformation of a special relativity, also known as Lorentz equations, as he was the first to write them down, although without understanding what they meant. These are going to be our most important tools in the remaining of the course. They will allow us to jump from one inertial frame to another, to agree what different observers measure. For simplicity, but without loss of generality, we will consider reference frame S at rest and reference frame S prime moving to the right on the x-axis. At time t equals to 0, both origins of coordinates coincide. So t equals to t prime equals to 0 and x equals to x prime equals to 0. You can think of it as having S prime coming from the left and moving to the right along the x-axis. When both origins of coordinates are one on top of the other, we set our clocks on. Galileo equations say for position, x is equals to x prime plus vt, and for velocity, u is equals to u prime plus v. Here I will call u to the velocity of that object I am tracking, and v will be for the velocity of the reference frame. But this second equation does not agree with the second principle of special relativity, that speed of light is the same for everybody. For instance, if we put c plus v here, we should still get c, same speed of light for everyone. So here we see something we need to fix. Remember, Einstein adopted the electromagnetic theory of Maxwell as the one to be satisfied, versus the equations of transformation of Galileo. I want to write the equation of transformation of the positions of an object as seen from two reference frames, S and S prime. I'm going to write the most general mathematical expression for the transformation of the x component. To do that, I need to consider that space is homogeneous and the transformation has to be linear, because this has to be generalizable to all the infinite possible inertial reference frames. A constant speed is going to be constant in all inertial frames. This mathematically means that the transformation needs to be linear. A straight line has to be transformed into a straight line. We can't include squares or other factors into the coordinates that we write in our equations. A straight line is in space-time diagram represents an observer or an object moving with constant velocity. The most general equation of transformation we can write is x is equals to ax prime plus bt prime, where a and b are constants to be determined. This is how we measure in the inertial frame S if we know the coordinates in the S prime inertial frame. We can reverse this equation, how we measure in the S prime inertial frame if we know the coordinates in the S inertial frame. X prime is equals to ax minus bt. Let's consider the case where we are observing the origin of the S reference frame, because the origin is always x equals to 0. From here, ax prime is equals to minus bt prime, or x prime over t prime is equals to minus b over a. But this happens to be the velocity S prime, the velocity of S prime with respect to S, v prime. So b and a are constants that tell us about the velocity of the inertial, moving inertial frame. Let's do the same from the other inertial frame. From S, let's observe the coordinates of S prime reference frame. Here, we have to impose that x prime is equals to 0, and we get that velocity is b over a. This makes sense, as the velocity of each reference frame has to be the same but opposite. Let's leave these results here for a moment and let's have a look at the coordinates of a beam of light traveling at light speed. For a beam of light, we know that x is equals to ct, but also x prime is equals to ct prime. Remember, light travels at c for all observers. Remember that we want to find the values of a, b, those are our unknowns. Those are the parameters that will define the transformational equations we want to find. We substitute these results for light in the general form of the transformation equations. For x we have, instead of x, I write ct, so ct is equal to ax prime plus vt prime. But substituting x prime, we get this equation equal to act prime plus bt prime. Factorizing this, we get that ct is equals to ac plus b times t prime. We do the same for the other equation. Instead of x prime, we write ct prime, so ct prime is equals to ax minus bt, which is equals to act minus bt. So ct prime is equals to ac minus b times t. I rewrite the first equation. I just swap the sides. AC plus b times t prime is equals to ct. And then I divide the first equation by the second equation. So AC plus b times t prime over ct prime is equals to ct over ac minus b times t. Here t's cancel and I get that ac plus b times ac minus b is equals to c squared. This is a well-known identity that can be written as a squared c squared minus b squared is equals to c squared. I have a relationship between the speed of light and the parameters I am looking for. So I am in the right path. Now let's go back to the results we found a few minutes ago and substitute back here and get that a squared c squared minus a squared c squared is equal to c squared. I solve for a, and I get that a is equal to 1 over square root of 1 minus beta squared. This, remember, we defined as gamma, an old friend of ours. Now that I have found a, I can easily go and find b, as b is equal to a times v. Let me write it here. So I have already found the transformation equation for x. X is equals to x prime plus vt prime over the square root of 1 minus beta squared. I left for you the exercise to find the transformation equation for t, which is t is equal to t prime plus vx prime over c squared over the square root of 1 minus beta squared. These are the Lorentz transformation equations, the key mathematical stones of special relativity. Let's read them. What happens if v is way smaller than c? Well, beta is almost 0, so this square root is basically 1, and we recover Galileo's result for the first equation. For the second equation, again, the denominator is 1, and this v over c squared is also negligible. This term is 0, and again we recover Galileo and Newton's idea of time being absolute for everyone. If v is important, we find that what we measure with our rulers and what we measure with our clocks depends on time and also depends on the position. Here space and time play the same game and both are relevant. Space and time are entangled and we can't treat them as separate entities. Look at this second equation and imagine you have two clocks on a fast-moving train. One at the front of the train and one at the back of the train. They might be synchronized as seen on the train, but as seen on the station they will not, as the times we measure depends on the time they tick on the train, but also on their position. What about y and z? How do they change the coordinates perpendicular to the direction of motion of the reference frame? Well, they do not. They are not affected. To see why this is so, consider two identical hollow cylinders. As seen by you, they are both approaching to each other with identical speed. So any contraction effect on the perpendicular axis will be the same for both of them. As seen from the cylinder on the right, that cylinder is at rest. So if there is going to be a contraction in that direction, then the cylinder on the left would fit into the cylinder on the right. But from the cylinder on the left perspective, it would be just the opposite. The cylinder on the right would fit into the cylinder of the left. So this doesn't make any sense, as they are contradicting results. There is no effect of relativity in perpendicular directions when we're talking about position. So now we have our powerful tools, and now we can apply them to specific situations to try and understand what implications all this has.